Now, a little bit of a digression. I would like to talk about the proof of Fermat's theorem, and in other words, how we know it's true. So I'm only going to sketch the idea, not every detail. But how do we know that Fermat's theorem is true for several variables? It's kind of a fun story, so I'd like to share it with you. So a reminder, Fermat's theorem for several variables is the statement that if we have a point which is a local maximum or minimum of f, then that point is a critical point of f, meaning that the gradient is 0 or undefined. How do we know that's true? So the idea is to take the vertical trace y equals b, and now you're looking at a curve which is the graph of z equals f of x b. So x is still a variable, but now we've set y equal to b to be a constant, and that graph has a maximum when x equals a, because for the variable x, when it goes through x equals a, it goes up to the top of this hill. AB is the top of a hill, right? And this is just one particular direction on the hill, but it still goes up to the top of the hill and then down the other side. So, imagine that you have a hill with a road going over the top of it, and you drive over the top of the hill and then down the other side. That's still a maximum along that road. So hope that helps visualize why it's still a maximum for that curve. And now, by the one-dimensional Fermat theorem, for one-dimensional meaning of a function with one variable, I mean, this is a function with one variable. So then the Fermat tells us that the derivative is 0 or does not exist. And what is that derivative? The derivative of the function f of x b, well, that's the function f where x is a variable and y is a constant. X is a variable and y is constant. So that's just the partial derivative. It equals 0 or does not exist when x equals a. So I'm taking the partial derivative when x equals a and y equals b. So that partial derivative is 0 or does not exist. Next, we can take the trace where not y. We just did y equals b. Now I'm going to take the trace x equals a and run through similar steps. So we're looking at the function where x equals a and y is a variable, and that has a maximum. It's still, in terms of our metaphor, with a hill with a road going over the top of it. This is the same hill, but just the road going over it the other way. Like, instead of the east-west road, now this is the north-south road over the top of the hill, but it still does go over the top of the hill and have a maximum. So that means that the derivative of that function is 0 or does not exist. And so the partial derivative of the function with respect to y is 0 or does not exist. And if you combine these things, the x derivative, both of them have to be true. This one was true when we looked at one trace, and this one was also true when we looked at the other trace. So they could both be 0 if if both of those traces were 0, and the only other possibility, I meant partial derivatives, if they're both 0, the only other possibility is that one of them doesn't exist, or both of them don't exist. But anyway, the only other possibility, they could, partial derivatives could both be 0, or one of them might not exist, and then the gradient doesn't exist, and that makes this a critical point. So that's the whole idea. All right, so that's a sketch of the proof of Fermat's theorem. I should have said in the first place that I was focusing on maximum. So we took care of the maximum situation. The minimum, well, that's a similar story, but with bottoms of valleys instead of tops of hills. So I think I'm going to skip that for now. I hope that this is enough to give you the idea of what's going on. So let's take a step back from the details. There were definitely some details that went into this. Let's take a step back from those details and look at the big picture. I think that we can take away two big ideas from this proof. Big ideas. And the first idea, which is maybe more of a medium idea, is a sort of bootstrapping, so to speak, because we used our 1D Fermat to get 2D Fermat. So we're sort of pulling ourselves up by our bootstraps. We're using our 1D knowledge to try to get some 2D knowledge. But maybe what's more interesting than that is the idea of slicing for dimension reduction. And that's a really, that's not what I meant to do. I wanted to highlight it because this is a major idea that is illustrated pretty nicely in this proof. Okay, we have a that's what I want. We have a graph of a function f of oh my goodness, f of xy. So we have the graph of this function f of xy, and it's a two-dimensional surface, but if we slice it with that vertical plane, that cuts it down to a one-dimensional curve. So we've reduced from 2 dimensions down to 1. And this is a big deal that happens all the time in mathematics and physics, engineering, sciences, taking slices or projections to reduce the dimension. If you've ever seen a cross-section diagram of something, that was a slice for dimension reduction. Well, that was probably reducing 3D down to 2D, but the same idea. So in fact, this is such a big idea that you've probably seen it 1,000 times already, but we also see it in this proof. Okay, well, that was the proof of Fermat's theorem, and that's how we know that it's true.